Alright, so hello and welcome. Here we are again. Gonna take another look at a problem. Also, happy Lord's Day. Hallelujah, praise God. Praise God. So this problem is the largest rectangle in histogram, hard C++ LeetCode. We'll give it a shot, see how we do. This problem is also, I'm going to try again to not use my glasses for some time and see how that goes. So you're going to see me leaning in very closely to the screen. This problem I'm certain I've seen before in some form. I think it's a stack-based solution. I think I already know how to solve this, but we'll try again. We'll also get an upvote also because I like this question. If it's what I think it is. Largest rectangle in histogram. Given an array of integers heights representing the histogram's bar height where the width of each bar is 1, return the area of the largest rectangle in the histogram. So you have a picture. So 2, 1, 5, 6, 2, 3, 2, 1, this looks like 11, 10, 11, 2, 3, 2, 1, 5, 6, 2, 3, and then the second one is, oh, excuse me, 10, yeah, between 5 and 6 is 10, I take it back, sorry, I understand now, yeah. So, yeah, I've seen a question similar to this before. This is sort of a stack-based solution. We'll talk about it for a moment. So, include, yeah, I can't see anything. This is going to be interesting. We're not going to modify the heights at all. Call them H as well. So this is similar to the sort of the trapping water question in that there is a clever way to approach this that makes this problem easier. So let me think about for a moment what the solution might be, what it might look like. So in your stack, yeah, so I think what you can do is you can take the width of the stack and multiply that by the no, exactly. How does it work? I want to say something like you could take the width of the stack and multiply it by the height you're looking at so far. So, like if you have first thing, the height, the width is 1, height is 2. You can take 2, right? 2 times 1. Then the next element you see, you can compare that to the height is 1, it's less than 2. And you can take 2 times 1 again. Then you see 5, you have 5 times 1. You also have 3 times 1. But you can't get, since 5 is larger than 1, you can't sort of, quote unquote, like, you won't be able to, I guess what you would do is, well, I'm actually not sure exactly what the algorithm should be, I'm thinking about it, but you can't compare, you can't use 2 anymore with 5. The best you could do is with the 1, right? And so that would be the minimum element you've seen up to that point, right? And then when you see 6, same thing you do. So 5 times 1 is 5. 3 times 1 is 3. 5 would be the best so far. When you see 6, you can do. You can't use 2 because the 1, right? But you can try the 1 again and do 4 times 1 is 4. And then there's also 5 times 2 because 6 is greater than 5. You could also do 5 times 2 as well. When you get to 2, you can do 2 times 3, and you can do 1 times 1, 2, 3, 4, 5, but you can't do anything with the 6 anymore. And then you see the 3, and you could do 1, 2, 3, 4 by 2, and you could do 1, 2, 3, 4, 5, 6 by 1. So these are all like the possibilities that you can have. I guess one idea would be you could push each of the heights into an array, or consider them in an array, and you could do a quadratic time algorithm. Now I'm fairly certain there's a way to do this in linear time. The constraints are expecting linear time, yeah, for the most part. Like I said, I've seen this question before. I just don't remember exactly how to solve it. But I'm fairly certain just some simple stack-based solution resolves. So you could go, I mean, you could do that if you wanted to. You can do like all of the elements from right to left from a certain point until, and I guess you would just sort of have like the minimum of all of these. So you'd want like all of the heights that have at least a 1 that are consecutive. And you can multiply, that's a number, and then all of the heights that are consecutive at least 2. So there's 1 here, that's 1 by 2, and then over here there's 1, 2, 3, 4 by 2, and then all the heights that are 3, there's just 1 consecutive heights that are. There's also another one here, 2 for 6, another for 4 and 5, right? Obviously you could just go right to 5, 10 here for the consecutive values, and then for 6 is only 1. So I guess one way of doing this would be like, for each height that you've seen, you want the longest consecutive sequence for that height. And if you multiply those two numbers, you can compare that to the return value that you want. So as soon as if you have 2, and you see, if you see things larger than 2, then you can update. Yeah, I remember this now. Yeah, actually, this is a really, really interesting problem. Yeah, I think I remember now. All right. So once you're looking at it, oh man, there's a really clever way to do this. I remember now. There's like a really clever way. I believe, but it's kind of tricky. Is it this one? I don't remember. Maybe it's not. I don't know. Well, let's say, okay, so if you see 2, then if you see something that's larger, then you can consider incrementing the position at 2. So you have at least one thing at 2. So basically what you would do is you could do like a cumulative graph type of thing where once you see something that's also 2 or larger, you can increment all of the positions, all of the heights below that, you can increment by 1. The problem with that, though, is you can't exactly do that, because once you see something that's like, if you go down to 1, and then you go back up to 5, you can't increment the 2 and the 1. You can only increment the 1 because the 2 is sort of behind the 5, something like that. Let's see. So, I wonder if I could just take a naive approach and then maybe optimize it. Maybe there's something like that I can do. So the naive approach would be, yeah, I guess for each number, you could do quadratic, or quadratic time is probably the simplest thing. So 2, there's nothing larger to the right of 2, so you just stop there at 1. Take that value, then you see the next value 1, however many previous values. So the previous value must be larger in this state or instance, I guess. And so you have 2 times 1, and then you can just kind of go all the way to the right until, yeah, you could just kind of go left to right from each point. So from 2, you stop at 1 immediately. 1, you go all the way. So I guess you can go, yeah, I guess you could go left and right. So 2, there's nothing to the left, you go to the right, stops immediately. 2 times 1 is 1. 1, you go to the left, you get 1. Go to the right, you get 1, 2, 3, 4. 1 plus 4 is 5 times 1, or yeah, well, there's also the 1 itself. So 5, 1 plus 1 plus 4 is 6 times 1 is 6. You get your 5, you go to the left, there's nothing to the left. To the right, there's a 6, so there's 1 to the right. 1 plus 1 gives you 2 times 5 is 10. 6 to the left, there's nothing, everything's smaller. To the right, everything's smaller, so it's just 6 times 1 is 1. 2, again, left and right, we get 1, 2, 3, 4. Times 2 is 8, and then finally 3, left and right, that's just 3. 3 times 1. Oh yeah, you could do it that way too. That also works. That's a quadratic time algorithm. Not the most efficient, but works. And now the idea is that maybe we can come up with something that's a little more clever, that allows us to perform those calculations without requiring, like, having to look backwards. Maybe let's start with that. Maybe we don't have to go backwards. So if we see something, larger to the right, that means the things to the left are smaller. We don't have to count them at all, right? On the left side. If we see something on the right side, and then obviously we're still going to accumulate things to the right, I guess. But we only care about things to the right that are at least as large. So also, if we get down to something smaller, we can also calculate our value so far. Something like that. And okay, so what does that look like in practice? So 2, there's nothing to the left initially. Go down to something smaller, nothing to the left as well. However, we would want to keep track of all the values we've seen so far, maybe, if we're going smaller. So yeah, I guess as you get smaller, you can multiply by the number of values in the stack at that point, the size of the stack at that, we'll call it a stack, size of the stack at that point. So 2, 1. So you would multiply what you have so far times the size, which is just 1 times 2, and then you go down to 1 and you do 1 times 2 again. But then you go larger, you could blow off everything in the stack you've seen at that point. The problem with that, though, is that 1 that you had, so you wouldn't blow it off. You don't count it for the 5, but you do want to count this 5 for the value you just saw. So this 1 you do want to calculate with 5. In fact, this 1 you'd want to move it all the way across. Let me think, how can we do both of those calculations simultaneously, where we're considering how many things to the right that are both larger than 1 and larger than 5 simultaneously? Because now you're calculating like 2 plus 1 and also 5 plus, so 2 plus 1 plus 1, and then 5 plus 5, right? And you want to do both of those calculations at the same time, where you get the correct amount in both instances. Well, and also interesting is this 2. We would no longer be looking for 5 and 6 at that point. That's kind of done once you go down. But you do still have the 1 there also. Like, you want to keep that. I guess what you could do, so what's interesting about that is when you push the 5 and the 6, you could hold off calculating the 1 until you're done. Right? You could hold off calculating the 1 until actually you get all the way through on the right side. So that's kind of interesting. So actually, I think it's a good idea to pop the previous values if you go down, I want to say. So if you have this 2, you go down to 1, you calculate that. That's all. Yeah, that'll be all the 2's up to that point, right? I think that's the way to do it. If you go down, you're going to pop that value, and then multiply that number by the number in the stack up to that point. Yeah, so you would say you'd see the next value. Take if it's smaller than the top, then take the top times the size of the stack up to that point, and then pop that value off the stack. Actually, you do that for every value that's smaller, that this is smaller than. You pop those all off. So you get your 1, then you go to 5, and that's, I don't know what you do if it's larger, greater than or equal. I'm not sure exactly what you do. I think you just push it on. So 5 you push on, 6 you push on. Get down to 2, you're going to want to pop 6, and you would do this number of things that are larger than 6 at that point. So that's not entirely true. Couple things there. A few problems there, like because you have that 1 there, that 1, yeah, actually, do you pop 1? Is the question. You don't pop 1, you pop 2. Well, and then push 1 on the stack. Part of the issue there is that this 1 has an additional value there, that additional 1 also. Presumably it's a monotonically decreasing sequence up to that point. Yeah, that's interesting. This might need to be a little more complicated than I'm letting on here. Again, I'm fairly certain this is not that complicated, but I don't know the answer. I have to think about it for some time. Let's see how we're doing on time. 17 minutes. Okay. Pretty sure once I get the idea, it'll be pretty straightforward. So no, it's not as simple as just. It almost makes sense to pop, but actually, the problem with that is when you get the smaller element, when you pop the 1, you want to get all of the elements to the left that are smaller as well, which is tricky. Yeah, so what you could do is you could have, when you push onto the stack, you could push some information so that you know which index you're working with. So for that 1, for instance, you can keep track of how many things to the left you saw once you saw the 1, things that were greater than or equal to 1 up to that point. That might be a good idea. So you push on your stack will have more than 1 piece of information on it then, something like that. So that 1, we know, even though you pop the 2 to place the 1 on there, you know that there's at least 1 element. There is 1 element to the left of 1 that's smaller, right? So you could sort of have like a 1, 1 there, I guess. Yeah, and when you see 5 is larger than the 1, and the other, yes, 5 is larger than 1. So you could push 5 on, there's nothing to the left of it, so it'd be 5, 0. And then push 6, that's larger than 5 as well. You can push 6, 0. Now what's interesting is 6 is larger than 5. You could, in theory, I guess you could update the 5, and then if you had like 7, you could update 6 too. So 5 would be like 5 times 3, 6 would be 6 times 2. And also update the 1. Now the trick is that the idea is that when you start popping these things, that's when you're going to calculate everything to the right of it. So so when we have 5 0, so we have 1 1 5 0 6 0, and then there's another element 2. When the 2 comes in, we've got to pop the 5 and the 6 and the 5. You pop the 6, there's just one thing. There's nothing to the left that's greater than or equal to 6, and there's nothing to the right, obviously. So you would, yeah, so that particular index that you're at right now, like that would tell you how many things to the right that are greater than or equal. There's really just one thing, right? Yeah, 6 and 6 is, there's, right, the index between what you're popping at the moment and 6, there's just one thing. So you could take that difference and say 6 times 1, compare that. 5, on the other hand, all the things that you popped up to that point from right to left would be greater than or equal to 5. So you can multiply 5 by 2 to get that. That's how you do it. I see. And then you get down to, so you pop 5, you pop 6, pop 5. You can use the current index and compare that to, really you could just count the number of things you've popped up to that point. I think that works too, because all of them have to be larger, or yeah, all of them, everything to the right, it's going to be monotonically increasing your stack, so everything that's to the right is larger. So you can just keep count of how many things you popped, and then you just add 1 to that count plus the thing you're about to pop. So you pop 5 times 2, and then you get down to 1, and now 2 is larger than 1, so you just leave 1. And the number of things to the left of 1 is 1, and the number of things to the left of 2 is also the number of things that you popped, right? So that 2, there was 6 and 5 to the left, so you get 2 2 now, until you're ready to pop 2. And then you get to the next value. Now, I might be wrong about how many things you pop. I could be wrong about that. I don't think so. Once you get to 3, because we're going to pop all 3. So once you get to 3, you just push that right on. That's 3 0, and then now you get to the ending index. And now the ending index, you're going to run another routine where you pop. So you pop 3, and you say, okay, there's nothing to the left, so there'll be 1, right? Difference in the index and where 3 is 1. So you popped one thing, that's 1. 3 times 1 is 3. Pop. So now you've popped 3. Now you look at 2. There's one thing you've popped, so you get 2. It's going to be, so the number of things you popped at that point, which is 1 plus 1 for itself, right? So that's 2 plus the things to the left for 2, which is saved. So 2 plus 2 times 2 is 4, right? That gives you 8, and then that's what you pop for 2, and then you're going to see 1. It's got to get popped, so everything gets popped down at the end. At 1, you're going to pop 1, and the number of things you've popped would be. So I think what you've got to do is add the number of things to the left of 2 that are greater than or equal to 2. You got to add that number to the number of things you popped. So you popped 4 things to the right, add 1 for 1, and there was something that 1 itself had something popped on the left. So you'd add 4 plus 1 plus 1 gives you 6. 6 times 1 at the end is the last consideration. I think that's the way to do it. I think it's a very straightforward, relatively straightforward approach. I think that works. I think that's correct. It's a little bit confusing, but I think that's the idea. There's probably a way to make it a little more clean too, a little bit cleaner. So we'll have a tuple. We're going to use tuples here. So hopefully I can code this well, even though I'm sort of blind as a bat over here. So we're going to say for int I equals 0, I is less than h.size. Actually, we're going to do less than or equal to. plus plus I, and we're going to say and we're actually going to use a stack instead of yeah, we're going to go ahead and use a stack. So standard stack of, we'll call these ints or tuples really, and we're just going to say vals or just st. We'll call it st. It's simple enough. So we're going to say if I is equal to h dot size, or h of I is greater than or equal to st dot top. Then we're going to say while. Well, actually, no, we should do spool check. So really, this is two different things. Yeah, we'll do two different things. So if we're greater than the size, then we're not going to check for the top at all. Else if h of I is, if this height is less than or equal, now is it equal to? I think it's strictly if it's less than. If it's equal, do we need to pop? No, so if we have duplicates, so if we had 5 and 5, I think you treat the second 5 like it's larger than the other 5, the previous. Because what's going to happen is you're going to say 5, that both of them are going to get popped, but when you pop that 5, it has, yeah, I think if it's less than or equal, you should pop the previous ones. I think so. So that way they're sort of unique, because you'll record the previously popped value. I think actually should be less than or equal to. So if that next height is less than or equal to the previous height, it's actually going to be st top. We could say if st dot empty, the stack is not empty. Right, also that's a tricky thing. The stack's not empty, and the top, if you say get 0 of the top. Yeah, so we have two different options. We have two different while loops we're going to perform. And we also have a ret value. You also have an issue of, oh, what are these numbers that we're multiplying, by the way? 10 to the 5th times 10 to the 9th, I think. 10 to the 5th times 10 to the 4th fits in an integer, so that's fine. Because we're going to, basically the maximum error you can get if it's just, everything's just maxed out. I just want to make sure that area fits in an integer. Just a consideration. So this is at the end, we'd perform all of the popping. We can do that in an if statement here. Actually, you know what we should do? We should actually just not do it that way at all. We're add an extra line of code to handle that. Yeah, an extra routine. So we'll do that at the end. If the stack's not empty, so there are a couple things here. If the stack is empty, let's do it that way. So if stack is empty, then we just push stack.push back, or push standard make tuple of, it's going to be the height, h of I, and 0. Right, haven't popped anything to the left. Else, if it's else, we can say auto t reference t equals st.top, and we'll say int top val or tval. It's going to be standard get of 0 of t. We're going to say if this value, t value, so if we're pushing onto the stack is less than or equal to, so if h of I is less than or equal to t value, then we want to, it's actually going to be a while loop we'll do. And then eventually we're going to push, st.push. And we're going to say, in this section of code, we could probably rewrite this to make this a little bit cleaner. We're going to say int popped 0, and we're going to start with have 0 here. So that's how many things to the left that we popped. And we're going to say if h of I is less than or equal to tval, then we're going to popped plus equals 1, popped plus equals more than just 1 plus the standard get 1 of t. We're actually going to pop t, st.pop, and we also want to say this is going to be and you can just say like x is h of I, the value we're considering. And then tval is then equal to, or you could just update t, reference t. I mean, instead of tval, you can just do standard get 0 of st top. That's maybe easier. Pop the 0, x is the height, while it's not empty, and this is at the top. Then we can say popped, pop the top, and actually I think that's it. I think you just keep popping elements off the top and adding them to the amount. Do you calculate those before you pop them? Yes. So what you're going to do is on ret, you're also going to have ret is so int possible, okay, or just say area. We're going to calculate this area. It's going to be popped so far plus 1 times this value of st top. You can actually just say like tval or tval. Pop times tval. So that's the number of things that are that you've seen from right to left, because these are monotonically increasing. So you can just keep adding this value. Popped plus 1 times that t value, and just say if ret is less than or equal to that, or less than that area, then set ret equal to that area. Then you're going to update popped to, excuse me, right, the number of things we've popped through on the left side. Add 1 plus whatever, however many is at that particular spot, how many things to the left of that had been popped for that value, and then you're going to pop the top, and then you just keep popping that and updating your popped value. So that's the routine, and then you push that at the end. And actually, you could do a little bit better than that, and you can say, you can actually put all of this in one loop, because if it's empty to begin with, right, then you don't enter the while loop and you'll just pop to 0. So you don't even need that. You can just make it as simple as this. And then at the end, you're going to say, you just run this same routine again. Like I said, I was thinking about doing that with like you could add this to, and I'm kind of not thinking right now. See if this compiles. I don't think this will be correct. Oh, this is just, wow, it's not empty at this point. Yeah, so what I was thinking about was like maybe running this routine one more time when I is at the height. Oh, this should be just st.top. Same thing here. I was thinking this should actually be 0, the t value. Anyway, I mean that's kind of unnecessary now. This t, oh, it worked. Hey, sweet. We'll just try a bunch of random values. This is kind of unnecessary to have here now. Yeah. Could just rewrite that. I was thinking about trying to figure out a way to write this where this loop just happens again if like I guess what you could do is you could say less than or equal, and then for x you could just update x, use a ternary operation, and say if x is oh, I know what to do. Yeah, I got an idea. You ready for this? I think I got it. We could do x here equals, and it's going to be h of I, or it's going to be -1. And that's if I is less than h.size. I think that works. And the rest of this we don't need. And I think this routine, right, all the heights are going to be greater than 0, or all non-negative. There we go. Sweet. So that's pretty concise. All right, let's try a bunch of different test cases. I can't see anything, so let's see, does it work? Invalid test case. Heights 10,000 it says for the height. Yeah, okay. One of these is more than 10,000, it's this middle one. Oh yeah. I think that's okay. Okay, let's see how we do. How are we doing on time? 40 minutes? It's kind of a while. All right, looks like it's correct. Nice. 1, 2, 3, 4, 5, 6, 7, 8. Where's their test case? 2, 4. Let's do 1. Let's do 0. Let's do 1,000. Let's do 1, 2, 3. Let's do 1, 3, 2. Let's do 2, 1, 3. Let's do 2, 3, 1. Let's do 3, 2, 3, 1, 2. And let's do 3, 2, 1. All those test cases, those are usually good to test. Those different permutations. Ooh, we got a wrong answer. Ooh, uh-oh. 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. Okay. Why did we get a wrong answer? Which one is wrong? Is it only the last one? Ooh, no. There's 3, 4 and 4, 4. 3, 4, and I didn't really identify that correctly, and then 4, 4. So it looks like 1, 3, 2. So let's see. I just want to make sure I don't release anything I should not. Incorrect. Incorrect answer. So I missed something important. My algorithm is not right. It's this one and this one, I think, are the two that are incorrect. Incorrect. Oops. These two. Let's see. Are these two? Or is it these two? Are these the two? Yes, these are the incorrect answers. Okay, so my algorithm does not work correctly for 1, 3, 2 and for 3, 2, 1. So 1, 3, 2, we should... I see. So I think the issue is... Well, I don't actually know. What's the problem? So 1 will get pushed, the area. We do 1 times 1. Then 3 is larger. I don't know. So we push 1. We don't check the area. We push 3. And we don't check the area. Nothing popped for 3. And then we push 2. 2, we have to pop 3. So we should get 3 times 1, right? So we get this popping. 3 times 1, and we don't push anything. Oh, we update the pop value to 1 plus 0, which is 1. So we popped one thing to the left of 2. And so now we have 1, which is 0, 2, which has 1, so 1, 0, 2, 0, or 2, 1. And then we get to the last value we pop, we get negative 1, it should be. So it's less than this, we do h of I. Now we should do negative 1. This is gonna should pop. 2. Its area is gonna be 1 plus 1. Oh, I did this wrong, huh? I see. You have to take, yeah, okay, that's interesting. So let's do this value. This is, this is right side, or right, It's actually not. It's actually left side. Or left amount, let's say. We'll just do left. Or left number. And it's actually going to be the left number. And then you update this. Add that left number. Is that correct? I think that's the issue. That's if the last value has, I think it's still the correct idea, it's just some cases don't quite work the way I was expecting them to. There we go. All right. I think that's it. We could do another test. There's 1, 2, 3, 4, 1, 3, 2, 4, 1. This is 4 factorial. There's 24 of these. This is going to take me a little bit of time to write, but I think that's okay. What do we have? I think we're done, but we can just keep testing. So 1, 2, 3, 4, 1, 2, 1. Actually 1, 2, 4, 3. I kind of missed that. 1, 3, 4, 2, and then there's 6 of those, I think. I don't know, 1, 2 has 2, 3 has 2, and then 4 has 2 as well. 2, 1. 1, 4, 2, 3, 1, 4, 3, 2. And then now you have, so those are the different options for 4, or for 1, and then you do the same thing with 2. So you do that 4 times, right? So I think you can copy paste these 6. 1, 2, 3, 4, 5, 6. And then swap 1 with something else. Swap the 1 with 2 in all of these, I guess. It's actually 1, 2, 3, 4, 5, 6. Let's do it that way. So 1 with 2, 1 with 2, 1 with 2, 1 with 2, 1 with 2. This is one way of doing this. And again, 1 with 2. Okay. And you can do the same thing again with 3, 3 with 1, 3 with 1, 3 with 1, 3 with 1, and hopefully I didn't make any mistakes. I think this works the way I'd like it to. I could be wrong. Hopefully not. I'm just looking for a way to do this a little bit faster to type. 4 with 1, 4 with 1, 6 times. Probably could write a script to do this too. Maybe that's a better idea to generate these values. This is just like a good test case to take a look at. Good sequence of test cases. Because it kind of handles that sort of monotonically increasing, decreasing stuff that happens. All right, I think we got it. I could be wrong, but I think we got it. I'll give it a shot. Hey, sweet. And we're relatively fast. Nice. All right, almost 90%. So that took a while, but we got there. How are we doing on time? It's looking like 50 minutes. Yeah, not too bad. We'll try again. This is probably like optimal, or roughly optimal. I don't know if you can really do this much faster than this. I mean, maybe you could do it faster without using tuples. That could be it. Yeah, if we somehow didn't use tuples, that maybe would be useful. You know what you could do? I got it. What you could push onto the stack, instead of pushing the tuple, you can push the index. Instead of putting the height, pushing the height, you can push the index, and then you can get the height from the index. So you can get the x value from the index. Yeah, that might be the way to do it. I think we could optimize this slightly. So we got it. That's wonderful. But yeah, that would be better on memory as well. Our memory is pretty good. Actually, our memory is really good. But we can do, and the deal is, if you can get the index, then you can calculate that quote unquote number popped value. Yeah, you could calculate that on the spot, I think. So let me just think. The number of things popped up to that point tells you what? It tells you how many things to the left that were popped. Is this okay? Is this reasonable? I'm trying to think. Can you do this with just taking the difference between where you are currently and how many things you popped off? That doesn't really give us the amount to the left, though. That's a tricky thing. So for instance, when we calculate 6, like when you put 6 on the stack, we're saying that there were a bunch of things to the left of 6 that we popped that were larger than 6. And that's what's being saved on top. The right side is not too hard to calculate, the stuff to the right. It's the stuff to the left that's tricky. I don't actually know. There's probably a cleaner way of doing this than using the way that I set the stack up here. I think this is a really simple way. To the left, we just keep track of how many things we popped to the left when we pushed this element on. You maybe could do, maybe you could just say the other index that's just below it. Yeah, so you could, yeah, okay, this is kind of interesting. So the index that's below it, if you take the difference between what you just popped and that index, that'll actually tell you how many things in between there were. Yeah, that's actually the way to do it. Yeah, let's try that. It's a different way of doing it. Also, I gotta get going soon. But there is that approach as well. I didn't think about that. That's kind of clever. So you can do another approach, which I'm pretty sure is the optimal approach. So you can just say integers. By the way, these integers only need to be, I think, they don't need to be integers. They just need to be 100,000, which is just barely won't fit in 16 bits. All right, that's fine. Okay, so we can do an int, and we can say x is h of I, that's fine, or -1. Okay, stack's not empty. X is less than or equal to, now it's going to be the stack top, which is h of stack top, because these are the indices. So it's actually, I don't want to lose my code in case I need to go back and fix it or go back and try again. Okay, so we're going to say top of the stack, h of the top of the stack. Then this left number we don't need any, but actually the way we're going to do this is First, we're going to pop. So the left number, we're going to call the pop first. Believe it or not, we're going to say int top index, or t index, is going to be st top. We're going to pop it. And we're going to say left number is not 1 plus the top anymore. It's going to be a ternary operator. It's going to be 0. And say if st top or is not empty. Now we're going to update left number. It's going to be the difference between the indices that we have now. So it's going to be t index minus, and these are both indices, so we can add 1, right? Minus st top. So if it's index 5 and that's index 1, 5 minus 1 plus 1 is 5 things. Yeah, so I think that's correct. I think that's the correct way to do it. You can take the difference between the indices and what's at the top and add 1. And actually it should start off at 1, I think, because itself is going to count. But yeah, so we pop first, and then we can calculate the area and take the left number. Also popped still is the same, by the way. So update populator to that left number. So yeah, so pop does keep going. Actually, this also could be calculated once. The popped, you could just take the difference between so that's the right to left, and then there's then where you started minus where you're at right now. Also, I think is relevant. Do we need to get the popped number anymore? Does that even matter? Now I'm thinking about it. There's that left number, popped plus that left number. The value that you're about to push on, you're actually not calculating anything for the value. This is just the ones that you're popping off that you consider. Yeah, I think you. I think you only need to. I don't think you actually need to calculate the popped amount anymore. Also, I should go back here. Just copy this here for a moment. Or actually, no, wait, hold on. Go back. Okay. Where's the right button? I gotta get going. We're gonna actually copy this. And then we're gonna go forward all the way back to where we just were. And we're gonna just basically remove or comment out what we just copy pasted, just so that I have it, right? And then now we're actually, I think we only need the left number times the x value. Yeah, obviously with -1 it shouldn't matter. But so actually no, this is so what's interesting here is this is t index. It's actually h of t index. H of t index. I think that's right. I don't know if we even need popped anymore. What happens? Does this compile? Start with that. Does it compile? You just push I. You just push I on there when you're done, which is fun. Okay, wrong answer now. Output, so we have too many numbers being added. Interesting. So I suspect maybe this is actually not a +1 here. Maybe that's wrong. What's wrong? I don't know. Nope. Definitely supposed to be a +1. So what's interesting is we're not using popped anymore. I think we might be miscalculating something here. Maybe we can go to like the lower test cases. We could see it. Or actually, the first test case should be visible. So for some reason we push 6, we get 12. So when you pop 6, what do you get? You get T index. So left number. When you pop the 5, actually, that's when you should get something interesting. So what happens when you pop 6? When you pop 6, you've got the index of 6 on the stack. You've got the index of 5 on the stack. You say x is less than or equal to the top, the height of the top. You get the, oh, that's what's wrong. Oh, I see. No, this is not t index anymore. This is the other one. This is actually the height of, is that right? It's the height of what you just popped. Or something like that. I don't know how to express it exactly. Runtime error, nice. It's actually, yeah, this is a little bit confusing. So the t index is the top, what's there, and you're gonna say once you pop, if there's still something in the stack, then you're gonna get this left number, and you can actually say it should be the index of it should be t index actually. I think that was right. I think that was correct. But for some reason we end up with too many things there. Maybe this is not supposed to be a 1. I don't think so. It's too small if we do it that way. For some reason we're not calculating yeah, I think that's the part that we're missing, the left side and the 5. So I think this is too high. So we take the top index minus what's at the top. The difference between the indices, yeah, we don't have to add 1 there. I think that is supposed to be, let me think for a second. It's 6050, 6 to 5, take that difference. That is a difference of 1. Which you don't include the 1 on the left. That's why you don't add the 1. So yeah, this is right. What's wrong though is we do need to actually add the popped amount. I think we do need to, because this is the number of things popped on the right. Which I think, okay, there we go. That's better. So some of these are wrong, but we got the ones we expected to be right, I guess. The simple ones. Let's go with the one all the way at the second to the last, the bottom. Yeah, so the idea here is if this is correct, then we can, if we're correct here, then we can This will be a much faster approach in theory. Oh, wait, what? Oh no! Oh no! Ah. Hold on. Forgot to... I actually can't see the keyboard, so it's a bit challenging. Okay. Second to last, this is why we have these test cases, because this is tricky. When you're dealing with like increasing sequences and stuff, you know, you definitely want to have like some test cases like this. Output 4, expected 6. Okay, so we get 4, 3, 1, 2. Excuse me, push 4, so pop 4, right? Push 3, pop 3 when we push 1. 3 we should do 3 times 2. So 3 to the left side is 1. The number of pop things. Pop things should start off at 1, I think, by the way. Because we only have one thing to the left side, and then you have itself. This maybe should actually be +1 then. Because actually that was all the stuff to the left. So wrong. What? When you push 3, you popped 4 and processed it. Now we don't know how many things were popped to the left. Oh, that's the issue. Ah, I see the problem. Ah, it's not empty. Otherwise, it's not. No, it's not 1. It's actually I. It goes all the way to 0. So it's t index minus really 0. I think that's the problem. Huh. Oh. 1 plus 1. Yeah. It'll be 2. That's interesting. 6 to 5. It's just 6. It's just 1. Take the difference, you get 1. If it's 6, index is 0. So 1 to 0 minus 0 is 1. But if it's a negative, something like a -1, basically, then you'd add 1. Yeah, that's kind of weird. Wouldn't have expected that. Would not have even thought about that. That's kind of a weird off by 1 error. All right, I think we're correct. That's a lot of test cases. It's probably correct if those all work. Hey, how do we do? 92%. Okay, not 100%, but a little bit faster than we had before. This popped part we can actually also calculate as well in one shot. We could probably remove. I don't know if you can remove this. I'm not sure exactly what you do here for this. We can remove this other stuff though. Other things. It's a little bit faster, not quite as fast as it could be. Well, we're pretty speedy. So I need to get going. How are we doing? Yeah, an hour and 10 minutes. Okay. Yeah, not as fast as it could be. We could actually, this popped amount, this could also just be this t index. So it's going to be the left side, take that difference, and also the difference between this t index and I, actually. So you could do t index minus I guess it would be, or I minus t index. So that's interesting because this left number is also this t index plus 1. So it's either minus the top. So we do minus t index. Hold on, what does that look like? Minus 1. It's probably minus t index minus 1. There you go. Let's try that, see if that works. Yeah, now watch this. This left number, it's 0, right? So this totally cancels if this is empty. But if it's not empty, so this left number is, so we could say something like the following. We'll say int n is going to be a ternary if st is empty. Then this is if st is empty, then this is I minus t index minus 1 plus t index plus 1, which is just I. Otherwise, it's I minus t index minus 1 plus t index, so these two cancel, minus the top, minus 1, which is, so it's I minus 1 plus minus st top. You can imagine that. And we can use n instead. There might be a better way to write this also, but we're trying to simplify this a bit. It's probably a better way to write this. There we go. Hey, so now we can remove this left number altogether. All right, how about that? We can just comment these out. Don't need this pop value either. Oops. All right, how about this? Does this still work? Hey, it's quick. That works. Still not much faster than what we had, though. That's kind of interesting. Doesn't really matter. You could do if st empty, we're going to say n minus equals st top plus 1. And just set this equal to 1. I think that works too. All right, let's go for it. There we go. That's a lot faster. 97%. All right, there's probably a way to optimize this even further. I don't see it offhand how we might do that. But this is a little bit better. I'm not sure how to avoid this one. You know, if it's empty, I mean, what are you supposed to do? If it's not empty, empty or not empty. So yeah, pretty neat. Pretty neat. We can get rid of the rest of this. I like this. This is definitely better. Not the best necessarily, but pretty good. Better than what we had initially. Yeah, over 90%. All right, not too bad. All right, we'll take it. So thank you for watching. Appreciate it. talk to you soon. Have a good rest of your day. I'm going to be late if I don't get going. So yeah, take care. Take care. This is fun. Yeah. Oh, it's taking me so much longer because of my